Hi, this is the MOSOMIC MEMS Microphone Guide. My name is MIKKO Suvanto. In this episode, I'll talk about the electrical implementation of digital microphones into devices. Stay tuned. This series is sponsored by Innovating Technologies. Digital signals are more immune to disturbances than analog signals. This makes the implementation of a digital microphone into a challenging electrical environment easier than what it would be with an analog microphone. This does not mean that implementing digital microphones is easy and can be done without proper knowledge of what to do. Also, a digital microphone needs proper supporting circuitry and protection from disturbances in order to get the best out of the microphone in terms of performance, signal quality and reliability. The basic needs of the microphone have to be fulfilled. It needs a stable and clean supply voltage. It needs a clean, low impedance ground. A digital microphone also needs a high quality clock signal that sets the timing of the digital interface. The design of the clock line circuitry and the components in it are critical factors in a digital microphone implementation. Naturally, the microphone needs an output signal path that is able to pass the signal through without degradation or added disturbances. Transmission lines have to be properly designed and executed to enable data transmission without bit errors or timing-related problems. The exact requirements depend on, for example, the electrical and electromagnetic hostility of the environment the lines are in, as well as the lengths of the lines. The goals and key implementation principles for digital microphones are pretty much the same as for analog microphones. I talked about analog microphones in more detail in the previous episode, so if you haven't seen it, it might be a good idea to check that first before proceeding with this one. The main differences between digital and analog interfaces are pretty obvious. The key selling point of digital interfaces is their superior disturbance immunity as compared to analog interfaces. There are only two signal levels in a digital signal, 1 and 0. Relatively big disturbances or problems in digital timing are needed to cause data errors in a digital signal, whereas even a minor disturbance can have a big impact on the quality of an analog signal. The better electrical robustness immunity of digital signals enables many benefits. Better signal quality, shorter device development times due to the reduction in design effort and design iterations. Problems related to radio frequency and/or electromagnetic phenomena can be tricky to resolve, requiring a string of redesigns and prototyping to optimize component values, circuit board layout, component locations, and so on. A digital interface can take care of many of the potential problems, so it may reduce the design effort and cost, as well as schedule delay risk, significantly. Another benefit is that the improved immunity enables having longer signal trace lengths. This is beneficial in larger devices, such as laptops, where microphone signals may have to be routed from the top of the display bezel and through the bezel hinge all the way to the audio codec or other system that receives the signal. Due to the better electrical robustness of digital signals, the results of disturbance filtering don't always have to be as precise as with analog signals. The more challenging the electrical and electromagnetic environment is, the clearer the benefits of digital interfaces can be. Improvements are clear, especially in wirelessly connected devices or devices used in hostile electromagnetic environments. One more significant difference between an analog and a digital microphone is that a digital microphone needs a clock signal to set the interface timing. The clock line has to be carefully designed to make sure the clock signal is clean and doesn't cause problems. Digital interface microphones also have some drawbacks as compared to analog interface microphones. Due to the analog to digital conversion done in the microphone, digital microphones tend to consume more current than analog microphones that have the same performance level. However, it should be noted that the analog to digital conversion has to be done somewhere in the system anyway, so the current consumption of the whole device electrical system may not be higher than with an analog microphone, even if the digital microphone component itself draws more current. Also, the interface itself consumes more current. Driving a signal line to switch rapidly between zeros and ones consumes power. The amount of consumption depends on clock frequency as well as the length and capacitance of the output signal traces. The prices of digital microphones are higher because of the extra component, analog to digital converter, needed in the microphone. However, it should again be noted that the analog to digital conversion has to be done in the device sooner or later, so in some cases the system level price difference isn't necessarily clear. The analog to digital conversion introduces some noise to the signal. Therefore, the signal-to-noise ratios of digital microphones tend to be a little lower than the SNRs of analog microphones with the same acoustic sensor. The differences are typically quite small. In digital microphones, the analog signal that would be output from an analog output microphone goes through one more operation, the analog to digital conversion. The analog output signal of the sound sensor may be amplified if needed, and after that the signal is filtered with an anti-aliasing filter. An anti-aliasing filter filters out frequencies that could otherwise cause artifacts or distortion when the signal goes through the analog to digital conversion process. The converter, ADC, is next in the signal chain. In MEMS microphones, the digital output format is typically PDM, pulse density modulation. Another digital interface possibility is I2S that carries a PCM, pulse code modulated, signal. In the case of PDM, the conversion method is typically a sigma-delta converter. After the conversion, the digital signal goes through the digital interface circuitry that configures the signaling for the interface. Typically, this includes determining on which PDM interface channel, left or right, the microphone transmits data. Let's have a look at the most popular digital interface in MEMS microphones at the moment, PDM. I'll save a closer look at PCM, I2S and other digital interfaces for a later video. Like I said, PDM stands for pulse density modulation. PDM is a relatively easy and inexpensive way to incorporate a digital interface and thereby better electrical robustness into a MEMS microphone. It's a simple 1-bit interface that's used in applications such as laptops, tablets, cameras and smartphones. The clock frequencies used in a PDM interface are fairly high, typically a few megahertz. The high clock frequency enables high-quality transmission of high sound frequencies. A PDM interface requires two interface signals, a data output and a clock. In addition to them, the microphone needs a supply voltage and a ground. The supply and ground can naturally be shared by multiple microphones. A useful and widely adopted addition to the interface is the left-right selection pin. It enables multiplexing, connecting two PDM microphones to the same data output line. The left-right selection pin enables choosing whether the microphone asserts data onto the data line on the rising or falling clock edge. The left-right pin of one of the microphones on the same data line is connected to the ground, and the left-right pin of the other microphone is routed to the supply voltage. A PDM microphone with a left-right selection pin has 5 contact pins on it: data output, clock, supply voltage, ground, and the left-right selection pin. Another common feature in MEMS microphone PDM interfaces is that the use mode of the component can be changed by changing the clock frequency. A common feature is a low power mode, in which the microphone consumes less current. The reduction in current consumption is achieved at the expense of microphone performance parameters, such as SNR or frequency bandwidth. Changing the mode of the microphone by changing the clock frequency naturally means that the device system must support multiple clock frequencies and switching between them. Even if implementing a digital microphone is easier and simpler than implementing an analog microphone, the basic principles for both implementations are still pretty much the same. The microphones must be electrically compatible with the way they are implemented into the device. The microphone components must be carefully chosen to make sure their performance and robustness are good enough for the system. The implementation should provide the microphone a good operating environment and circuitry that enables getting the best possible performance out of the microphone. This means a reasonable environment what comes to electromagnetic radiation and as disturbance-free supply voltage and ground as possible and feasible with the help of separation from disturbance sources and disturbance filtering. This is as important as with an analog microphone. The signal path for the output of the microphone must be designed to preserve the quality of the signal what comes to noise level, dynamic range, distortion and phase. A significant difference to analog interfaces is that the dynamic range is hard limited by the digital interface. When the full-scale digital level is reached, the reduction in signal quality is catastrophic, unlike with analog microphones. Another difference as compared to analog microphones is that the frequency range of the microphone system is limited by the clock frequency. I'll talk more about this in the next episode. The variation caused by component tolerance and the device production must be taken into account. The signal path must be optimized in terms of disturbances with proper subsystem placement, layout, shielding and disturbance filtering. Separate audio systems from other noisy systems like digital circuitry, RF systems and high-power signals to prevent disturbance and noise coupling. Shielding the signal traces from electromagnetic radiation and from capacitive conduction from other signal lines is a good idea also with digital microphones. There are analog signals inside the microphone and they must be shielded with a Faraday cage built into the microphone package. Just like with analog microphones, the cage should extend to the inside layers of the device circuit board and protect the signals all the way to the system that receives the microphone output. There should also be disturbance filtering on the signal lines. Keeping the supply voltage and ground clean is especially important. Grounding is important also for digital microphones, just like it is with analog microphones. Proper grounding reduces signal quality problems such as RF disturbances, signal crosstalk from other traces, and increased noise. The purposes of ground are the same: to provide a return path for the currents flowing in the device, to act as the reference voltage for the signal, and to provide a place to direct unwanted high-frequency disturbances from the microphone-related signals. Just like with analog microphones, all free circuit board area should be filled with ground. The rules are looser for digital microphones than for analog microphones what comes to the layout of the circuitry and the components on the circuit board, the placement of microphones in the three-dimensional space inside the device in relation to noise sources and in relation to supporting circuitry such as power supply and ground. The rules are looser also what comes to the distance to the system that receives the microphone output signal. Not having to keep signal traces short is one of the key selling points of digital microphones. Also, the proximity of other signal lines to digital signals and the risk of signal coupling is not a big concern with digital signals. Another benefit of digital interfaces is that they are not susceptible to ground voltage fluctuations between the microphone and the receiving system. Let's have a look at some guidelines for designing the signal connections in a digital microphone system. I use PDM here as an example interface, but the same rules pretty much apply to any digital interface. In addition to the general guidelines I just listed, there are a few important things related to filtering and terminating the lines around a digital MEMS microphone. The four key component groups used for disturbance reduction and signal quality improvement are capacitors, inductors, resistors, and ferrites. These components help keep signal lines clean of disturbances and to make sure that the properties of the signal line are compatible with the properties of the signals and components on those lines. I'll go through some things here and some I'll save to episode 20, in which I dive deeper into electrical implementation and disturbance mitigation. Filtering capacitors act as bypasses for high-frequency disturbances on signal lines. Typically, filtering capacitors are used on the supply voltage line to prevent disturbances in the supply voltage that could affect microphone signal quality. How much of the disturbances on the power supply pin of the microphone actually turn into disturbances in the microphone output signal depends on the power supply rejection (PSR) performance of the microphone. Several different value capacitors, for example 3 of them, may be needed to make sure all disturbances are filtered out effectively. The capacitances vary typically from 10 picofarads to 10 microfarads. The circuit layout for the capacitance connections is important. The lengths of the capacitor traces should be as short as possible. Also, trace inductances should be minimized to avoid any unwanted changes in the way the filters work. A series resistor or ferrite can be added on the power supply line of each microphone. They can further improve power supply disturbance cleanliness. The job of source termination resistors is to match the impedances of the source and the trace and thereby avoid interface timing issues. Termination is especially important when lines are long. The resistors are connected in series with the signal trace, as you can see here in the illustration. They're placed as close as possible to the source, in this case the microphone for the data line, or the source of the microphone clock signal. Component values have to be chosen to match the trace. Typical values for source termination resistors in a MEMS microphone system are somewhere between 50 and 100 ohms. Termination resistors on the microphone output data lines, RTD in the picture, prevent interface timing problems and thereby data errors. The resistors on the clock line, RTC, help avoid overshoot and ringing when the clock signal switches from 1 to 0 or vice versa. Clockline termination resistors reduce the risk of interface timing problems and disturbance emissions. The ability of MEMS microphones to tolerate clock overshoot varies from microphone to microphone. The resistors may also reduce the amount of current consumed by the interface. There are a few more things related to the layout and connection routing in digital microphone systems that help make the system more immune to disturbances. The same principle applies for analog connections around a digital microphone, namely ground, supply voltage and left-right selection, as for all analog microphone lines. They should be kept short. This should be kept in mind when laying out the connections from the left-right selection pins on the microphones to the supply voltage or to the ground. If keeping them short isn't possible for some reason, the system designer must somehow ensure that the signals remain clean. This can be done with, for example, disturbance filtering. All the analog signals should be separated from disturbance sources, such as other analog or digital signal lines, RF systems and so on. If necessary, appropriate shielding, such as ground planes or ground traces or complete Faraday cages, must be applied between the microphone lines and disturbance sources. Even though digital signals are robust against disturbances, it's still a good practice to keep the microphone clock and data lines physically separated from potential disturbance sources such as RF systems and high-speed transmission lines. Okay, that's it for this episode. In episode 19, I'll continue talking about the electrical implementation of digital microphones into devices. More specifically, I'll talk about the digital clock, interface timing, I/O levels, and also the characteristics of the digital microphone output signal path. I hope I'll see you around. Cheers! If you have any comments or questions, write them down in the comments below and I'll do my best to answer them. You can also contact me online or on social media. If you like what you saw here, give a like for the video and subscribe to the MOSOMIC channel. That way you help me reach more people and thereby create more content. If you need more in-depth microphone training than what you saw here, contact me and we can arrange it. The training can be adapted to suit any interests and skill levels, and the customer can choose the location and duration of the course. MOSOMIC provides also consultation services in all things related to MEMS microphones. If you're a microphone buyer, I can help you select the right components for your product and manage your microphone suppliers. I can also assist in implementing the microphones into your device. For microphone manufacturers, I provide microphone marketing, product definition, product management, and development management services. I can also help you create all kinds of MEMS microphone documentation,